Welcome to my channel. In this video, we are going to discuss about the objective type question and answer from the topic Quarterwave transformer from the subject transmission lines and waveguides or transmission lines and RF system. So in this, that is the Quarterwave transformer, it plays a very important role in the impedance matching in transmission line. Okay, so in order to provide the impedance matching in transmission line, so we may use this Quarterwave transformer, Quarterwave line as a one thing, and we may use stub matching. In stub matching, either we may use signal stub matching or double stub matching. So these are all the various methods in order to perform the impedance matching, in order to provide the impedance matching in transmission line. So in this video, we are going to discuss about the Quarterwave transformers. So you see, a Quarterwave transformer is dash. Okay. So the Quarterwave transformer, it is nothing but it's a segment of transmission line near the load end, which is equal in length to 1/4 of wavelength. That is the length of the Quarterwave line. Why the name is Quarterwave line means the length of that Quarterwave line is lambda divided by 4. Okay. So this Quarterwave transformer, it is nothing but a segment of transmission line near the load end, which is equal in length to 1/4 length, okay, of the signal of the line. Then the next one, the impedance inversion. Okay, impedance inversion at radio frequencies may be applied with the help of an dash. The impedance inversion at a radio frequency can be applied using half wave line, short circuited stub, Quarterwave transformer, open circuited stub. So using Quarterwave transformer, we may provide the impedance inversion of the radio frequencies. Then the next thing, a Quarterwave transformer can be considered as a dash. Impedance inverter, impedance doubler, tripler, quadrupler. So the Quarterwave transformer can be considered as an impedance inverter. That means it can transform. Okay, so it is used as an impedance inverter. That means it can transform low impedance to high impedance, as well as the high impedance to low impedance. Okay. Then the next thing, which transmission line is called as 1-to-1 transformer? So the lambda divided by 2 transmission line. Okay, the half wave line. Half wave line means the transmission line is having the length lambda divided by 2. It is called as a half wave line. So this half wave line, it can be act as a 1-to-1 transformer. Okay, so in half wave line, it repeats its terminating impedance. Okay, that is whenever the length is equal to lambda divided by 2, the input impedance is equal to load impedance. Okay, so that's why it is considered as a 1-to-1 transformer. Then the next thing, what is the condition for Quarterwave transformer? So what is the condition for the Quarterwave transformer is the Z0 squared. Okay, that is the characteristics impedance square. It is equal to the product of Zin and ZL. Okay, this is the condition for Quarterwave transformer. So that means the characteristics impedance is Z0 equal to square root of Zin into ZL. Zin is the input impedance, ZL is the load impedance. Okay, so the characteristics impedance is the geometric mean of input and load impedances. This is the required condition for Quarterwave transformer. Then the next thing, find the characteristics impedance of a Quarterwave with input and load impedances given by 50 and 25 respectively. So here what is the question means, for a Quarterwave line, the input impedance and load impedance is given. The input impedance is Zin equal to 50 ohms and the load impedance is ZL is equal to 25 ohm. So the question is that we have to find the characteristics impedance. Okay, so already you know the relation between the characteristics impedance, input impedance and load impedance of the Quarterwave transformer. Okay, so this is a very important 2-mark problem. So Z0 squared is equal to Zin into ZL. Okay, so you know the relation. So in this, Zin is given, ZL is given. So you just substitute the values. So Z0 squared is equal to 50 into 25. So 1250. From that, the characteristics impedance Z0 can be calculated by, it's a square root of 1250. So the answer is 35.35 ohms. Okay. So the characteristics impedance of quarter wave line with input and load impedance 50 and 25 is, the answer is 35.35 ohms. So this is an important question. So in this problem, so there may be here the load and input impedance is given. Characteristics impedance we calculated. Okay, so instead of load impedance, input impedance, there may be a chance to in the problem Z0 and ZL is given. We have to find out input impedance, or Z0 Zin given. We may calculate the ZL. Okay, so there are three ways of the different problem is that. Okay. The next question you see, find the load impedance in a quarter wave transformer with the characteristics impedance is 75 ohms and the input impedance is 200 ohms. So in this question, we have to find out the load. Okay, is that L value we have to find out. So what are the two data given? Characteristics impedance Z0 is given, and one more thing, input impedance is given. Okay, so you know the formula for quarter wave transformer, Z0 squared is equal to Zin into ZL. So from that we have to find out ZL. So if you are rearranging, the ZL is equal to Z0 squared divided by Zin. Okay, so what is Z0? 75. So 75 squared divided by Zin is 200. So if you are calculating, we will get the answer is 28.125 ohms. Okay. So this is the load impedance of the particular quarter wave transformer. So this is a second type of question. And the third type you see, the characteristics impedance of quarter wave transformer with the load and input impedance is given by 30 and 75. Okay, so here the load impedance and input impedance is given. We have to find out the characteristics impedance. Okay, so as usual formula, Z0 squared is equal to Zin into ZL. So you just substitute. Then if you are taking square root of this answer, we will get Z0 is equal to 47.43 ohms. Okay, so this is the answer. Then the next question, the third type of problem. So question you see, find input impedance of quarter wave line with characteristics impedance 50 and load impedance is 20. Okay, so this is the third type of problem. Here the question is, we have to find out Zin. Okay, so what are the data given? Z0 given, ZL given. So from that you just rearrange. What is the Zin? The Zin can be written as Z0 squared divided by ZL. So what's the value of Z0? Characteristics impedance is Z0 50 ohms. So 50 squared divided by 20. So we will get the answer is 125 ohms. So 125 is the answer. Okay, then the next question, the group delay of the wave with the phase constant is 62.5 and the frequency 4.5 radians per second. So here, what is the question means? We have to find out the group delay of the particular wave. That a wave with the phase constant beta. Okay, phase constant means you know it's a beta. The beta value is 62.5 and the frequency 4.5 radians. So radians means which frequency? This is not a f, this is a omega. So beta value, omega value is given. The question is group delay. Okay, so already you know the formula for group delay. What is the formula for group delay? The group delay TD equal to, okay, TG. The group delay is equal to beta divided by omega. Okay, phase constant divided by frequency. So you just substitute 62.5 divided by 4.5. So we will get the answer as 13.88. Okay, so 13.88 is the answer. Then the next question, the characteristics impedance of a transmission line is normally chosen to be dash. Okay, so generally how that is what is the characteristics impedance of a transmission line? So the characteristics impedance is normally chosen as either 50 or 75. Okay, so normally it is chosen as 50 ohms or 75 ohms. Then the next thing, identify the material which are not present in the transmission line setup. Waveguides, cavity resonator, antenna, oscillator. So the oscillator is not used in the transmission line setup. Okay, in transmission line setup, we have to use the waveguides, cavity resonators. For transmitting and receiving the signal, we have to use antenna. Okay, but there is this oscillator is not present in the transmission line setup. Okay. The next thing, with reference to transmission line, the normalized load impedance is determined by dash. Okay, what is mean by normalized load impedance means the load impedance value is at L divided by the characteristics impedance is at naught. Means it is said to be the normalized load impedance is at Ln. Okay, so the normalized load impedance means we have to divide the particular load impedance by the characteristics impedance of the particular transmission line. So dividing the load resistance by characteristics impedance of the line is called as normalized load impedance. Okay. Then the next one, a 50 ohm transmission line is terminated in a load impedance of 50 plus J100 ohms. So the normalized load impedance is dash. Okay, so here you see a 50 ohm transmission line. So what is this 50? This 50 is said to be characteristics impedance Z0. So the Z0 value is 50 and the load impedance ZL. ZL equal to 50 plus J100 ohms. So the question is normalized load impedance. So what is mean by normalized load impedance? This load impedance divided by Z0. It is said to be the normalized load impedance. So 50 plus J100 divided by 50. So we will get 1 plus J2 ohms. Okay, this is the normalized load impedance. Then the next one, a quarter wave transformer is useful for matching any load impedance to transmission line. The statement is true or false. It's a false. A quarter wave transformer is useful for matching any load impedance to transmission line. This is the false statement. The quarter wave transformer, what is the reason means? The quarter wave transformers are a simple circuit that can be used to match real load impedance to a transmission line. So using quarter wave transformer, we may match only real load. Real load means the resistance. Okay, purely resistor. If the load is purely resistor means that load can be matched with the transmission line. Okay, so the quarter wave transformer cannot use it to match the complex load impedance to a transmission line. So that's why the statement is false. Okay, so quarter wave transformer is, you just remember, the quarter wave transformer is used to match the real load impedance to a transmission line. That is, for example, RL. Okay, RL is matched with a transmission line. If we want to match the complex load impedance. Complex load impedance means R plus J omega L. That complex load impedance cannot be matched with the transmission line using this quarter wave transformer. Then the next thing, the major drawback of the quarter wave transformer that it cannot match complex load to a transmission line. Okay, it cannot be overcome. So, you know, the drawback of quarter wave transformer, the quarter wave transformer is it cannot match the complex load to transmission line. Okay, it is yes, but it cannot be overcome. This is wrong. Okay, so we can overcome. So the major drawback of quarter wave transformer, it cannot match the complex load to a transmission line. Okay, but that problem can overcome by transforming the complex load impedance to real load impedance. So we may transform that complex load impedance to real load impedance first, then we may use the impedance matching. Okay, so that's why this statement is also false. Then the next thing, complex load impedance can be converted into real load impedance by dash. Okay, so in order to convert the complex load impedance ZL into the real load impedance RL, we have to use which step? Okay, scaling down the load impedance, introducing an appropriate length of transmission line between load and quarter wave transformer, changing the operating wavelength, none of the mention. So in order to change the complex load impedance to real load impedance, we have to introduce the approximate length of transmission line between the load and quarter wave transformer. We may change the complex load impedance into real load impedance. Okay. Then the next thing, converting the complex load into real load for impedance matching has no effect on the bandwidth of the match. Okay, this is a true or false. This is a false. Okay, that is, if you are converting complex load to real load in an impedance matching, it has no effect on the bandwidth of the match. It's a false. Okay, that is, if you are adding the length of line to a transmission line, then it alters the frequency dependence of the load. So that's why the bandwidth is also altered. So if you are converting complex load to real load, automatically the bandwidth of that particular thing is also changed. Okay, so that's why this statement is false. Then the next thing, the major advantage of quarter wave transformer is dash. It gives proper matching, it gives high gain, broader bandwidth, none of the mention. Okay, so this quarter wave transformer, it provides broader bandwidth. Okay, that is the major advantage of quarter wave transformer. So the quarter wave transformer can be extended to multi-section design in a methodological manner to provide a broader bandwidth. Okay, so we may use, instead of single transformer, we may use a multi-section transformer in order to provide the broader bandwidth. Then the next thing, if a narrow band impedance match is required, then more multi-section transformers must be used. This is a true or false. Okay, if narrow band impedance matching is required, we have to use multi-section transformer. This is the false. Okay, if narrow band impedance match is required, means we may use single section quarter wave transformer. Okay, but for wide band impedance matches required, we have to use multi-section. Okay, if we want to provide the narrow band impedance match, a single quarter wave transformer is enough. If we want to provide the wide band impedance match, we may use multi-section quarter wave transformers. Then the next thing, if a single section quarter wave transformer is used for impedance matching at some frequency, then the length of the matching line is dash. So you see, the single section quarter wave transformer is used for impedance matching at some frequency, then the length of the matching line is different at a different frequency. Okay, the length is different for different frequencies. The next one, the quarter wave transformer cannot be used for non-TEM line for impedance matching. Okay, it is a true only. The quarter wave transformers, it cannot be used for non-TEM line impedance matching. Okay, for non-TEM impedance matching, this quarter wave transformers cannot be used. The next thing, the reactance associated with transmission line due to the discontinuities, okay, due to the discontinuities can be ignored, have to be matched. Discontinuities do not exist, none of the mention. So the reactance associated with the transmission line due to the discontinuities have to be matched. Okay, so the reactance due to discontinuities in the transmission line contribute to the impedance. So they can be matched by altering the length of the matching section. So by altering the length of the matching section, so we may match the transmission lines. Okay, so these are all the some of the questions from the quarter wave transformer from the unit 3. Okay, so the unit 3 is a impedance matching in high frequency lines. Okay, so in the next video we are going to discuss about the single stub matching and double stub matching and what is the use of the Smith chart. Okay, so thanks for watching this video, and please subscribe my channel for more videos, and please share this video to your friends also. Okay, so thank you. We will meet in the next video.